Okay, so now that I finally got my ice40 board to work, it's time to redesign my 486 motherboard. So mainly what I did, I took the XC2C128 CPLD off of it, and I replaced that with a PCI slot. All of the signals that it needs to run the CPU are on this slot. It's just on an external card now. So this means that I can use a ice40 FPGA, or if it turns out that that doesn't work for some reason, then I can make a new one and swap out the card without having to make a new motherboard. The reset logic is going to have to change because the FPGA takes time to start up, boot up, read its data, start working. And it's actually got a C done signal, like a signal that it outputs a 1 on whenever it's ready. So I need to incorporate that into the system reset somehow. Or I could just, manually play with jumpers when I get it wrong, which is probably what I'll end up doing, but I bet I can get this to work. I mean, I had the automatic reset circuit actually working on this current iteration, so I bet I'll get it working. Um, yeah, so here's the layout. It's going to be pretty much the same as the old layout. Here's those new voltage transceivers I added. This reset stuff is going to change a little bit. Here's that PCI slot. I just moved some chips over, moved the RAM up here. It should work. I'm continuing to go with the ATX-like form factor. There is another type of form factor that people sometimes use. It's where you have a modular backplane, and then the CPU itself is on an add-on card, and then all of the system peripherals, such as keyboard controller and all these MISC chips, pretty much everything except the ROM, like they're on their own card. And the advantage of this is you can interchange parts of the system without having to remake any circuit board, without having to remake circuit boards as often. I'm not going to do that this time, but I want to get that in the future. Mainly what I'm waiting for is I need to get ISA working, industry standard architecture, the 16-bit expansion slots. 16-bit expansion slots are kind of complicated, and it's there's a lot of pins on it. There's 98 pins, and they all have to have their own voltage transceivers and all this stuff. So the only way for me to do that is with a second FPGA, because the ones I work with only have 144 pins. I am aware that they make BGA ice40 chips that have up to 256 pins, but BGA components are just too hard to solder together, so I'd rather not use them. Okay, here's a schematic for the ice40 board that I made. I didn't change that much stuff to finally get it working. It's complicated. You're just going to have to read the post on my website for all the details. But mainly, I'm just going to go over, I'm going to give you a quick summary of all of the stuff that I did wrong. So, over here, this voltage regulator, see this resistor? It goes to ground. That actually needs to go to 3.3 volts. Because what you're doing right now is you're putting a 0 on the enable pin, which tells it to turn off. So you have to put a 1 on there. So that's why that has to be 3.3 volts. Um, Programming it was hard. Yeah, programming it was pretty hard. It just took a lot of trial and error until I finally figured out what had to be done. So, first off, I tried Arduino. That was just too hard. So I switched to a FT2232HL breakout board with a USB port on it. So you have to use that, and then you have to use either iceprog or flash ROM. And those are kind of the only two programs that are robust enough to be suitable for this. And then you have to connect the programmer ground, like the ground pin on the programmer, and the ground pin on this device. Like they have to be connected together because doing that improves the signal quality just enough that it'll work. I was able to program it at 750 kilohertz roughly when I plug it into the computer. But the way this works, if you read the documentation, is that when you're not programming it, the FPGA has to read from this ROM. And you can't control the speed that the FPGA reads from the ROM, as far as I know. And in my case, the FPGA was reading it at 6.1 megahertz. And basically, I guess I just got lucky that it worked, making that the fastest digital signals that I've ever seen on anything that I made and still work. So that's pretty good. If the FPGA would have tried to read that at 16 megahertz or 30 megahertz, like, yeah, I'd still be trying to figure this thing out. Okay, another thing right here. This diode. Um, there's a lot of options. If you look at other people's schematics, like there's all kinds of different diodes that people use. Some schematics don't even have a diode here. The thing that worked for me is I found you have to put a 1N418 diode right here. And that's the thing that made it work. Okay, so it's gonna be kind of hard to see what's going on here, but bear with me. I have this thing loaded up with a program that I made in Verilog. It's a very simple AND gate test, but as you can see right here, these two resistors are putting a high signal on both of the inputs, and this is the output. So there's two ones going in and there's a one coming out. Now if I take this resistor and put it to ground, so I'm inputting a 0 and a 1, well now the output of that AND gate is false and the light turned on, or I turned off. And now if I put this resistor back, then now it's outputting a 1 again. So this test right here proves that I finally got it working. And that's pretty much all I have for today. Thanks for watching. Bye.